Hey guys, what's going on? Today we're going to be talking about HBase. So HBase is an open source, distributed, highly scalable NoSQL database that sits on top of Hadoop as a storage layer and is modeled after Google's Bigtable. So it stores data as key value pairs. So HBase is a column-oriented database, which means it stores different columns separately on disk. Now, actually, HBase has the concept of column families. So column families are basically columns that are grouped together as a column family, and they're stored separately on disk as a means of being able to perform operations more efficiently and quickly on these column families for big data. And data is indexed by rows, row keys. It can be accessed with low latency, and it can be updated with low latency as well. We have horizontal scalability, which means you can scale out by adding in more servers. So you have data in HBase that is partitioned and is replicated across many different servers. We're going to be seeing more of how it does this in a bit when we talk about the architecture. Alright, so this is the data model for HBase. We have a row key which uniquely identifies a row. You have column families and column qualifiers. A column family basically groups many different columns together. So we have name, which is a column qualifier, age is a column qualifier. Both of these come under the students column family. Likewise, we have branch, which is a column family. We have bname and GPA, which are column qualifiers, come under the branch column family. And you have data that's stored as bytes. It's untyped data that stores a sequence of bytes, unlike it is in traditional databases. Cell values can have multiple versions, so we can specify to have multiple versions. By default, it's going to have up to 3 versions. And even when you retrieve data, you can specify how many versions do you want to retrieve. Well, if you want to retrieve a specific version, if you don't specify, it's going to return you the most recent one by default. All right, so that's it for the data model. Moving on to the architecture, you can see that it follows a master-slave architecture. It sits on top of Hadoop. Right, we have a master node, and we have the worker nodes, which are region servers, right? And we have Zookeeper as well. So Zookeeper, HMaster, they work together in order to ensure that there's high availability, there's fault tolerance. So Zookeeper keeps everything synchronized, right? And it also makes sure that there's high availability. So what do I mean by that? So let's say the HMaster goes down. We want to make sure that there is another HMaster, secondary HMaster, which becomes a new active HMaster, right, to take its place. So there's no single point of failure. Same thing goes for region server. In case this region server goes down, we want there to be a secondary which becomes this active, which takes the place of the region server, basically, to make sure that there's high availability. And what are regions? So data in HBase is split into chunks, which are called regions essentially, and they're distributed across different region servers. They're managed by region servers, right? Okay, and how do we know where are the locations of these regions, right, or these chunks of data? For that reason, HMaster keeps something called a meta table, right? A meta table keeps track of which data lives where. So in the case that client makes a request to HMaster, it uses the meta table, right, to find out where does that data live, and then go ahead and retrieve that data or perform any operation that the client wants to on that piece of data. Okay, and what else does the region HMaster do? So HMaster also assigns regions to region servers. So assigns which region server stores which chunks of data, right? So when there's a new region server, right, when you want a new region server, it would assign regions to those to that region server, and it also is responsible for making sure that when a region grows too large, you want to split that region, right? Don't want a specific region to grow too large. It makes sure that that region gets split into further separate regions or chunks of data. Okay, now let's have a look at how does the region server work. What are the responsibilities of the region server? So a region server, as we talked about it before, it sends heartbeats to Zookeeper to ensure high availability. In case that the region server goes down, we want to make sure there's another region server which takes the place. And it uses something called an LSM tree structure for low latency read and writes. Now let's talk about it. What is an LSM structure? Okay, so this is essentially what goes on inside of a region server. So region server manages reads and writes, right? So client requests a read or write to a specific chunk of data or region, right? Region server is what handles this reads and writes. It does this using something called an LSM tree structure, which we're going to discuss, which we're going to discuss about right now. So what's the first thing that happens when, let's say there's a write request? What's the first thing that happens? We write that change into something what's called a write ahead log. A write ahead log is a separate place on disk, which is a log structure, right? It's an append only structure, right? It's an append only structure. We keep adding to it, right? It's immutable. And it basically keeps track of all of the changes that are made to this data, right? In case that this data goes down, you still have your write ahead log, which kept track of all of the changes that happened to your database, which happened to your data, and you can basically replay these changes to get back the data in the correct state, right? So this is sort of a failure or backup recovery sort of mechanism, right, that you have. And then we have what's called a mem table, right? So first of all, we write it to write ahead log, right? This is for backup. And then we have a mem table. Right? What's a mem table? A mem table is basically a structure in memory, right? It's a data structure in memory. And HBase uses what's called a skip list, right? A skip list for its mem table, or the data structure that it uses for its mem table, which is called a skip list. It has O of log n time complexity for search, insert, and delete. And these are the operations that will happen normally. You would want to search something here in the mem table, you want to insert something or delete something. And how does it? It happens pretty fast, right? So O log of n is in memory. So when you want to write a request, it gets written onto the mem table, right? And the thing about in-memory storage is that it's limited, right? You cannot store everything forever in memory, right? So the way the LSM tree structure works is that first of all, you would, if there's enough space in the mem table in memory structure, you would write information onto the mem table. Right? If there's no, after it reaches a certain point where you can no longer write in memory, what happens is that it takes all of the data that is in this data structure in memory, and it flushes it to the disk. Right? It flushes it to the disk, and how does it flush it to the disk? It's basically a traversal. You basically traverse this structure, and because it's already sorted, it's a skip list. A skip list is a sorted data structure, much like a binary tree, but it's a bit different, right? So it's already sorted data in memory. All you have to do is traverse it, which would traverse it and write it to memory sequentially, which is an O of n linear time operation. So you take all of the data from mem table and add it to what's called an SS table, or in this case, it's an H table, right? It's an H table. H table is basically what represents the data that gets flushed from mem table onto the disk, and you have multiple of those, right? Multiple H files or SS tables, and they are sorted, right? They will be sorted, right? They're lexicographically sorted, which just means they're sorted alphabetically, or they're sorted based on the row key, right? They are sorted on the row key. So here I give an example. Let's say we have 30, 40, and 50, right? These are, let's say, the row keys, and it will be sorted like this. This is something, this would be something what, this is an example, a very simple example of what an SS table might look like. So you have row keys 30, 40, and 50, right? And you have data associated with those row keys. Okay, so LSM trees does further optimizations to make this more faster. So a small recap, what did we just discuss? Whenever there's a write request, we write it to a write ahead log. This serves as a means of backup, right? We keep track of the changes that we're making to the data, and we write this change, right, which would have a key and some values associated with it, right? We care about the key, so we're gonna write it to a mem table, right, which is a skip list. Like a binary tree, it's a sorted data structure. We store the data in memory in a sorted fashion, right? And then we can just flush it onto disk, which will again be sorted, right? So it's sorted in both places, which makes it fast to search. So in case we need to search for data, we would first of all go to the mem table, right, in memory, and we would search for it, and again Just to mention again that search has a time complexity of O log n, which is pretty fast. In case it doesn't find it in memory, it has to go and search inside of the SS tables, and because it's also sorted, right, it will be sorted in order based on the row keys. We can still search on it fast. We can use something called binary search, which has a time complexity of O log of n, which is pretty fast. And LSM trees does further optimizations, which we're going to talk about. So it does something called sparse indexing, which it keeps a separate table to keep track of which row key has which memory location. So for example, you have, let's say, 30, 40, and 50. So what's going to happen is it knows that from 30 up to 50, these are the memory locations. And let's say I'm searching for 40. It knows that, okay, between 30 and 50, there's 40. So it's probably going to be in these two ranges. And I have to search only for the first half of the table. I don't have to search the other half. So I hope that makes sense. Sparse indexing, you just keep a separate table which keeps track of ranges of the row keys and what memory locations are they stored in. So it can cut down the search space, right? You need to search only for specific ranges. And a Bloom filter is a data structure which basically answers whether let's say you're searching for a row key, it's going to answer you whether that row key or the element exists in this set or not. Basically, that's going to save us time, right? Because there can be multiple SS tables. You're going to have to look through them one by one. And let's say it doesn't exist in this, no, so you can move on to the next table instead of spending time to search through this table, right? That will save you read and write read operations. Those are the optimizations that the LSM tree takes care of. This is what we discussed just now, right? So whenever there's a write, the reason server handles read and write requests. This is the reason server, and you have a region. First of all, the request goes to a mem store, right, which keeps track of what all changes are happening to the data, and then that gets written. Once you can no longer write to mem store, that all of the data gets flushed to the disk, which stores an H file, and a region node is usually co-located with a data node. A data node in HDFS is essentially a storage node, and that will get replicated across different servers. So that's how the replication is taken care of. Region splitting and compaction, as we discussed before, these are things that happen in the background. So once the region grows too large, you want to make sure that HBase is going to go ahead and split that. When we talk about architecture, split that further into separate regions. And there's something called compaction. Compaction means these SS tables, when there's too many of these, right, there will be duplicates across these different SS tables, which is not good. What happens is that we want to essentially compact them or join them together to reduce the number of search tables, so it will be faster to search through them, and there will be fewer duplicates that way.